All right, for our last review session for 111, what I thought would help would be I'll take an old final. So I think I already sent you one final to practice from with video solutions from that. So here's the second. You got all the, probably more stuff than you even want to practice from. Your final will look like this. I mean, yes and no. Same basic idea, same layout, same concepts, but not necessarily same problems with different numbers. So anyways, what you will see is your final will start out with a bunch of true-false statements, just like these two. The first few here are dealing with rational functions, which are these things that kind of look like polynomials divided by polynomials. On this test, these rational functions will only show up in the true-false. That's also how I wrote your exam. So in your exam, there's several of the true-false statements will deal with rational functions, kind of like these first four right here. And then you won't see them again for the rest of the exam, just like you don't see them again here. I think that's true. Okay, so for this first one, it says, true or false, this thing has a horizontal asymptote at y equals -5/2. In this case, that's true. The way you figure that out is by you look at the degree of the numerator and the degree of the denominator. If the degree of top equals the degree of the bottom, then what happens is you get a horizontal asymptote at the quotient of the leading coefficients. So what I'm saying is this -5 divided by this 2 tells me where the horizontal asymptote will be, but only in the case where the exponents are the same. These are both 6 here. If these weren't both 6, that would not be the case. If the one up top was bigger, then there'd be no horizontal asymptote. If the one on the bottom was bigger, there would be a horizontal asymptote at 0. It wouldn't matter what the coefficients are. But when they're the same, the quotient of the coefficients tells you where the horizontal asymptote will be. I better go quicker or I'm going to spend 5 hours on this video. Next one, this function has only one x-intercept. To determine the x-intercepts, what you want to do is write it in its factored form. This is how you determine the x-intercepts, this is how you determine the holes, and this is how you determine the vertical asymptotes. Everything except for horizontal asymptotes. So x-intercepts are the values of x that make the top equal 0, the bottom does not equal 0. In case you were wondering, holes happen when the top is 0 and the bottom is also 0. Holes, aka removable discontinuity, I think that might be what your book uses. And vertical asymptotes happen when the top is not 0 and the bottom is 0. So in this case, let's see, x equals -2 will make the top equal 0, but it will not make the bottom equal 0, so that's an x-intercept. You might be like, what about x equals -1? That'll make this 0. Yeah, that's right, but it'll also make the bottom 0. So you have a hole there, what's called a removable discontinuity. And then x equals +1 is a vertical asymptote. This is the only x-intercept. This function has one x-intercept. That's a true statement. This function has a vertical asymptote at x equals 1 and x equals -1. That's false. The reason that's false is vertical asymptotes happen when the top does not equal 0 and the bottom does equal 0. So in this case, let's see here, -1. -1, yeah, it makes the bottom 0, that's true because of this factor, but it also makes the top equal to 0. So we do not get a vertical asymptote at x equals -1. We get a removable discontinuity, aka a hole. It's a false statement. This function has a horizontal asymptote at y equals 0. Turns out that's true. The reason that's true goes back to the argument I was making up here when I was talking about horizontal asymptotes. You get a horizontal asymptote at y equals 0 anytime the degree of the denominator is larger than the degree of the numerator. Anytime that happens. Numerator. Because it's in its factored form, it's a little bit hard to tell what the degrees of the top and the bottom are. Yeah, you could FOIL these all out and figure out, get them so they look more like a polynomial like up here. But you don't have to do that because all we care about is the degree. If you FOILed this one times this one, you'd get an x squared. And then you multiply that by this one, you get an x cubed. The degree of the top is 3. On the bottom, x minus 1 to the 7th power, that means multiply x minus 1 times itself 7 times. The degree of that's already 7. Multiply by this, the degree equals 8. The degree of the bottom, which turns out is 8 in this case, is greater than the degree of the top, which is just 3. I guess I should be consistent. If I'm going to use bottom here, I should use top here. If I use denominator, I should use numerator. Next one. Complex numbers. Wait, I thought complex numbers were just something on the first midterm. You said the true-false statements were only going to cover things since the first midterm. True, but complex numbers popped up again in the second half of the class when we talked about complex roots. And when you're dealing with complex roots, you do have to multiply by conjugates, so something like this could have shown up. This statement's false. Why is this false? We'll try to FOIL this thing. Okay, if we were going to multiply these guys together, let's see. First, the f in FOIL. 3 times 3 is 9. Outside, 3 times negative 2i is negative 6i. Inside, 3 times positive 2i is positive 6i. And then finally, last, 2i times negative 2i. A negative times a positive is a negative. 2i times 2i is 4i squared. Negative 6i and positive 6i, those cancel out. So I'm left with just 9 minus 4i squared. But I squared equals negative 1. So really what I get is 9 minus negative 4, which is the same as 9 plus 4, which is 13. 13's not 5. This is false. Okay, if x equals 5 is a root of a polynomial, then the graph of that polynomial has an x-intercept at negative 5, 0. That's false. It has an x-intercept at 5, 0. Roots are the same as x-intercepts. You're like, no, there was something where it was positive, I make it negative, right? It has an x-intercept at 5, 0. It has a factor, or how about x minus 5 is a factor? This is parenthetical. X minus 5 is a factor. So maybe that's what you were thinking about. Maybe you weren't thinking about that with the positive and the negative thing. But if 5 is a root, 5, 0 is an x-intercept. That's really the end of it right here. This mess, its vertex is a local minimum. Well, you could try to sketch this thing all out, graph it, take a look at it, but you don't need to. Turns out this is false. The reason I know this is false is because the leading coefficient is negative. And so essentially, if you completed the square, if you wrote this in our standard form, you'd have a negative number out in front of the x minus something squared. And that negative is going to flip things upside down. What I'm saying is the parabola f of x equals x squared, its vertex is a minimum, but this negative kind of flips things over. This is negative, so vertex is a max. And the last one, I to the 5th power equals I. Turns out that's true. Kind of weird. Here's the argument. I to the 5th is the same as I squared times I squared times I to the 1st power. 2 plus 2 plus 1 is 5. But I squared is negative 1. So what I get is negative 1 times negative 1 times I. Negative times negative is positive. I just get I. Hope the Ducks, I guess that's true. They did win. True. They beat Texas. This is old. No longer makes sense. What would make sense here? Some stupid question about basketball, maybe. It's basketball season. Or baseball. Baseball's coming up. March Madness, the tournament. Whatever. Moving on. Average rate of change. This does show up on your test. Make sure you can take the average rate of change of whatever function I give you. So the first thing to know about average rate of change is the average rate of change formula. It's basically just your slope formula. You could think about it like this, or you can think about it as this. Because f of x is just the same as the y. Whichever one makes sense to you. So all we got to do is take this function right here, figure out the 4 values, these 4 or these 4, Plug them in, simplify, we'll get our average rate of change. So it gives me two of those values. It tells me x1 is a, and it tells me x2 is a plus h. If I know x1, I can figure out f of x1, in other words, y1, by taking this thing and putting it into my function. F of x is 4x squared minus 7x. F of a would be 4a squared minus 7a. F of a plus h, well now instead of replacing all the x's with a's, I'm going to replace all the x's with a plus h is. It's kind of hard to say, but all I'm getting at is that where I used to see an x, now I see an a plus h. That's it. So I take these four values, plug them up into this formula. y2, 4 times a plus h squared minus 7 a plus h, minus y1, 4a squared minus 7a. Note the parentheses. I'm subtracting. I want to subtract this entire thing. I want to subtract all of y1. This whole thing is y1. I need the parentheses, so I subtract it all. Divided by x2, given to me as a plus h, minus x1, given to me as a. This big mess, simplify it. Why? Turns out this is calculus. This is what you'll do when you take a calculus class the very first week. You'll be dealing with the average rate of change, and not just average rate of change with numbers, but specifically when one of your points is a and the other is a plus h. You're not supposed to understand what this means at this point. At this point, it's just a jumble of symbols that you're pushing around on a page. But this thing will end up being very important when you take a calculus class. It's called the difference quotient. Some books call it the definition of the derivative. Well, it's not really the definition of the derivative according to the book we use, but pretty damn similar. Anyways, you don't care about all that. You just care about how to simplify this thing. On the bottom, a plus h minus a. Well, a and negative a cancel out. I'm left with just h. On the top, a plus h squared is the same as a squared plus 2ah plus h squared. So I got 4 times that mess minus 7a minus 7h. Note that I wanted to subtract this entire thing. Minus 4a squared plus 7a. Again, I want to subtract this entire thing, distribute the negative sign through. So if I take this 4 and distribute it through, I get 4a squared plus 8ah plus 4h squared minus 7a minus 7h minus 4a squared plus 7a. You got to be kidding me. Well, this will actually simplify. These will always simplify pretty nicely. 4a squared minus 4a squared. Cool, those cancel out. 7a and negative 7a. Those cancel out. Nice. What do I have left? It looks like just these 3 terms. I got 4h squared. I got 8ah. And I got 7h. And I got an h on the bottom. Because I have an h in each term in the numerator, I can factor out an h from each of these 3 terms and cancel it with this h here. If I did that, I'd be left with 4h plus 8a minus 7. This has a very big meaning in math, just not in any math that we've seen so far. So for now, this is just our answer. It's just something. It's just the average rate of change simplified as much as we could. But in another class, it's really important. Okay, find all values of x such that f of x... Okay, I put this on there because these b and c look the same. Okay, that's not true. They look similar. Right? B and C look pretty damn similar, and people confuse them. So I put them both on. I put them on your test too, I'll be honest. So this one is saying f of x, this thing that's given to me, it's given to me as 4x squared minus 7x. That thing is equal to negative 3. F of x equals negative 3. Not to be confused with f of negative 3, which is saying take this f of x, and everywhere you see an x, change it into a negative 3. So f of negative 3 is 4 times negative 3 squared minus 7 times negative 3. But before I get down here to part C, let's deal with part 2. Part 2, how about part B? This is an equation. I can solve this equation. And when you have an x squared and an x, you're going to want to factor. See, the way I'll factor, it only helps to factor if your equation set equal to 0. So let's first add 3 to both sides of the equation. You get 4x squared minus 7x plus 3 equals 0. And then factor this thing. I don't know how many steps I should show here. I want to factor 4x squared minus 7x plus 3. A couple different ways to do this. There's this guess and check method, or there's this 3-step process. I think that process is a little bit easier. You can do it however the hell you want. If you're doing the 3-step process, what you do is you first look for two numbers that add to negative 7, the coefficient on the x term, and multiply to 12, because 12 is this 4 times 3. So I want two numbers that add to negative 7, multiply to positive 12. If you think about that for a little while, you'll get negative 3 and negative 4 as those two numbers. So then what you do is you replace negative 7x with negative 3x and negative 4x. You haven't factored this, you've just rewritten it. Instead of in 3 terms, you've written it in 4 terms. The advantage is by picking these 4 terms in the way we did, this will always factor by grouping. The way you factor by grouping is you look at the first 2 terms, look for the greatest common factor. In this case, it's an x. If you factor out an x, you're left with 4x minus 3. You look at the next 2 terms, you have to factor out something so that you'll be left with 4x minus 3. I almost have it already. I have negative 4x plus 3. If I factored out a negative 1, I'd be left with 4x minus 3. I now have 2 terms that both have a 4x minus 3 in them, so I can factor out that 4x minus 3. This is gone, this is gone. All I have left is x minus 1. So all that factoring was so that I could rewrite this. Instead of 4x squared minus 7x plus 3 equals 0, I got 4x minus 3 times x minus 1 equals 0. This is much better than this because the only way you can multiply together 2 things and get 0 is if the first one equals 0 or the second one equals 0. Change one equation into 2 equations. These 2 equations are things I can solve. Add 3 to both sides, divide by 4. Add 1 to both sides. I get 3/4 and positive 1 as my 2 answers. And then we started C already. The basic idea on C was just not confusing it with B, basically. Negative 3 squared is positive 9. Negative 7 times negative 3 is positive 21. 4 times 9 is 36. 36 plus 21 is 57, which is our answer. Part D, function composition. Compose 3 functions together. I gave you one on your test where you compose 3 functions together, so make sure you can do this. The basic idea is instead of writing it in this form, start by writing it in this form. Then start replacing functions with what they're equal to from the inside out. What I mean is the innermost layer here, I have this f of x, but I know that f of x is equal to 4x squared minus 7x. So what I can do is I can say, really, this is the same as, instead of writing f of x on the inside here, I'll write 4x squared minus 7x. And now the next layer I want to replace this f right here. Well, I know that f of x is 4x squared minus 7x, but I don't want f of x. I want f of this thing right here. So what I'm going to do is I'm going to copy f of x. I'm going to copy this thing up here, except instead of writing the letter x, I'm going to write whatever is inside these parentheses. So I'm going to write 4, and then instead of x squared, I'm going to write what's inside those parentheses. 4, here's the thing playing the role of x, squared, minus 7 times that thing playing the role of x. So this is f of 4x squared. So I still have this f on the outside, which I no longer have room to write. There we go. So I replaced this level, and now I just have one f left. So again, I know what f of x is, but I don't want f of x. I don't want f of x. I want f of this mess. So I'm going to copy f of x, this guy up here, 4x squared minus 7x, except instead of writing the letter x, I'm going to write this mess. What I'm saying is 4x squared minus 7x. Except instead of writing x, I'm going to write what's inside these parentheses. In this case, it's 4 times 4x squared minus 7x. squared minus 7 times 4x squared minus 7x. And then again over here, instead of writing x, I'm writing what's inside the parentheses. 4 times 4x squared minus 7x squared minus 7, 4x squared minus 7x. You might imagine that you could spend forever simplifying this. You could. Fortunately, I say don't. Leave it just like this. That's fine. Number 3. Express this parabola in vertex form. You're going to see a problem like this. It's going to be a lot like this, just with different numbers. It's going to ask you for more or less the same things that you're asked for here. This one I give a hint. I tell them what C should be when it's in this form. I didn't give you this hint. One other thing I should mention. This might look old, number 2. Is that true? No. On this final, what I gave you on your final is the first problem is something off your first midterm. Okay, I probably should have started with this. Actually, I'm going to write this in the email, so never mind. The first problem is going to be true-false stuff. The second problem is going to be a problem off your first midterm. The third problem is going to be a problem off your second midterm. And then there's going to be 4 more problems, which will be second half of the class stuff. One of those problems will look kind of like this one, to tell you the truth. One of those problems will look kind of like this one. So what you want to do on this problem, there's a couple different ways to do it. I think the easiest way to do it is first, instead of f of x, write y. So I'm going to be doing a lot of algebra, some pretty tricky algebra. And so I want to be able to move pieces around, and it's easier to write a y than an f of x. F of x just looks confusing. Next thing I want to do is complete the square. We can only complete the square if I have the x squared and the x term all by itself, and the coefficient on the x squared term is just 1. So first I need to get rid of this 15. Let's subtract 15 from both sides of the equation. Then I need the coefficient on the x squared term to just be a 1. Right now it's negative 4, so I better divide both sides of the equation by negative 4. That gets me here. Then I want to complete the square. So I have to find some number that I add to both sides of the equation so that this becomes a perfect square. Let's jump up here. In this case, that number that I'm going to add to both sides of the equation is positive 1/4. I'll show you where that comes from in just a sec. Really where it comes from is it's the number that will make this a perfect square. This is a perfect square right here. It is x plus 1/2 squared. Okay, I can see that, but maybe you couldn't see that this is the same as this. Let me explain how you can get from here down to here. Once you get to this stage where the leading coefficient is a positive 1, call the coefficient on the x term, give it a name, call it b. So maybe in this case I'll say b is equal to just 1, the coefficient on the x term. The thing that you add to both sides of the equation is always going to be b over 2 squared. That was this 1/4, and that was this 1/4. Don't look for b up here. We called b 1 down here. We couldn't start completing the square until we added 1 as our leading coefficient. These 1/4 came from taking this 1, dividing it by 2, getting a half, and then squaring that, getting a 1/4. This number down here will always be this. It'll always fit this form. X plus something, and that something will be b divided by 2. b is positive 1, so I want x plus 1/2. X plus 1/2 squared. What I just did was I completed the square, which is something that we've seen a little bit in this class, but it's been a little while. You could clean up the left-hand side if you want. I'm not going to, because I want to solve for y, so one way to solve for y would really just be undoing all these steps that we did. The last thing we did was we added 1/4 to both sides, so let's now subtract 1/4 from both sides and get y minus 15 over negative 4 equals x plus 1/2 squared minus 1/4. You're like, what happened to this 1/4 right here? If you did x plus 1/2 squared, if you FOILed this all out, you would get a 1/4. That 1/4 got sucked up inside here. This negative 1/4 I got from subtracting 1/4 from both sides of the equation because I'm trying to solve for y. If I were trying to solve for y, get this y all by itself, the next step would be to multiply both sides by -4. That's exactly what I'm going to do. If you multiply both sides by -4, this is a little bit tricky. There's two terms here. This is one term, this is my second term. So that -4 has to get multiplied by each of these two terms. I have to do -4 times this first term, and then -4 times this second term. -4 times -1/4 is +1. We're almost done. Add 15 to both sides. I get this. This is a mess, but the advantage here is you could graph this thing. You could think about this as it's just transformations as the function f of x equals x squared. Right? This plus 1/2 moves it to the left by 1/2. This plus 16 moves it up by 16. This -4 flips it vertically and stretches it by a factor of 4. We can come up with the graph because we have it written in this form. And sure enough, it said to write it in this form, and the c should be 16, which it looks like is what we got. You could change this y into f of x if you really felt like it. I don't feel like it. I'm not gonna. Vertex. You find the vertex in a couple different ways. If you have vertex form, you can just look at this thing and tell that the vertex is at -1/2, +16. How did I get that? Because think about the shifts. The vertex of f of x equals x squared starts at 0, 0. This -4, it'll stretch it, it'll flip it, it won't move the vertex at all. But this plus 1/2 will shift the vertex to the left by 1/2. In other words, it'll make the x coordinate of the vertex move from 0 to -1/2. This plus 16 will shift the vertex of the graph, up 16 units. So the y coordinate of the vertex, which used to be 0, is now +16. It'll always be this number and this number, except the negative of this one is the new coordinate of the x. Find the x-intercepts of this parabola. X-intercepts happen when the height equals 0. The height is the f of x. So what you can do is you can set this equation equal to 0 and solve. You can do that. You'll get the right answer. But it might be easier since this is the exact same as this. It's just a different form. Take advantage of all that work you did. Instead of setting that top one equal to 0, let's set this one equal to 0. Let's say 0 equals -4 times x plus 1/2 squared plus 16. The reason why this is easier is up here I have x squares and x's. Down here I only have the letter x written one time, so I can isolate it. Subtract 16 from both sides of the equation. Actually, instead of subtracting 16 from both sides, let's add this negative term over to this side and get 4 times x plus 1/2 squared equals 16. Divide by 4. X plus 1/2 squared equals 4. Take the square root of both sides of the equation. X plus 1/2 equals, when you take the square root, make sure you put in a plus or minus. So x plus 1/2 equals plus or minus 2. X equals -1/2 plus or minus 2. I'm fine with you leaving it like this. Or if you'd rather write it, you could say -1/2 plus 2 is 3/2. -1/2 minus 2 is -5/2. I don't care which way you write it. Either one of those is good. Those are the x-intercepts. If I happen to ask you for the y-intercept, it's much easier. X-intercept happens when y equals 0. Y-intercept happens when x equals 0. So take your original equation, either use this one, or it'd be even easier to use this one, and make all the x's 0. That'll give you the y-intercept. Didn't ask for the y-intercept on this specific test, but maybe I ask it on your final. Rational root test. All right, so the rational root test tells you that all possible rational roots come of the form factors of the constant term divided by, I should say, integer factors of the leading coefficient. And then you want a plus or minus. And since I'm putting a plus or minus here, I don't care that it's -2. I can just write 2. because I'm already taking care of the plus and the minus over here. So factors of 4 are 1, 2, and 4. Factors of 2 are just 1 and 2. So I need to make up some fractions where the numerator in the fraction, give myself a little bit more room, is one of these 3 numbers, and the denominator is one of these 2 numbers. So 1 divided by 1, or 2 divided by 1, or 4 divided by 1, or 1 divided by 2, or 2 divided by 2. But wait a minute, 2 divided by 2, that's just 1. I already have that on my list. I don't even need to write it again. Or 4 divided by 2. Wait, that's the same thing. 4 divided by 2 is just 2. I already have that on my list. Here are the 8 possible rational roots. Now it says, test those rational roots till you find one that works. What do you mean by works? Well, these are just possible rational roots. One of these is an actual rational root. What do you mean by an actual root? Well, root is the same as an x-intercept. An x-intercept happens when the height equals 0. So what I got to do is I got to figure out f of these 8 values. One of those 8, f of that value will be equal to 0. Plug those 8 things into the function, figure out which one equals 0. I don't want you to spend all day plugging in numbers, trying them until you find one that works. So I'm going to either make 1 or -1 work. I did that on this test. I'm going to do the same thing on your test. So start by testing 1. Don't start by testing 1/2. Start by testing 1. Let's see, that would give me -2 times 1 cubed minus 6 times 1 squared plus 4 plus 4. That's -8 plus 8. That equals 0. Hey, look, my very first try, I found one that works. Works means f of that equals 0. What I'm saying is 1 is a root. Had I gotten any number other than 0 here, that would mean 1 was not a root, and I'd have to try another number. I would have tried -1 next. Because I'm telling you, I will make either 1 or -1 work. I promise. Get 1's a root. Now it says find all remaining roots. So I keep testing the rest of these numbers until I find one that works? No, because we don't know that the remaining roots are rational numbers. Rational numbers are numbers that you can write as a fraction. The remaining roots, they might be square root of something. They're not even in this list right here. So instead what you do is you say, because 1 is a root, x minus 1 is a factor. Because x minus 1 is a factor, x minus 1 is going to divide evenly into my polynomial, -2x cubed minus 6x squared plus 4x plus 4. There's a problem like this on the final. Not the exact same, it's a different polynomial. Same basic idea, same steps. Do polynomial long division. When I do polynomial long division, I better get 0 as my remainder, because if I get 0 as my remainder, that means this divides evenly into this. In other words, this is a factor of my original polynomial. And I know that it's a factor of the polynomial because I just figured out 1 was a root. So let's do polynomial long division and hope we get 0 as a remainder. If we don't get 0 as a remainder, we screwed up. So I want to get rid of -2x cubed. If I put a -2x squared up here, then when I multiply it by this x, I get -2x cubed. I take -2x squared times -1 and I get positive 2x squared. What I'm saying is write something up top here that you will then multiply by this guy and write down here. And your goal is to cancel out the far left column. -2x cubed minus -2x cubed goes away. -6x squared minus 2x squared is -8x squared. And bring down the 4x. This is where everyone makes a mistake. People write a 4x here or a -4x, or they somehow screw this up. It's always, you're always subtracting. -6 minus, some people even go as far as to write something like, I'm always subtracting. Let me write this like this so I remember that I'm subtracting. -6 minus 2 is -8. Now you repeat. Same thing, right? Something up top, but now instead of trying to get rid of -2x cubed, I'm trying to get rid of -8x squared. The way I'll do that is by putting a -8x up top. -8x times x is -8x squared. -8x times -1 is positive 8x. This is a good time to tell you that if you learned how to do synthetic long division instead of polynomial long division, fine. I don't care. You can do either method. They both give you the same thing. 4x, careful, we're subtracting, minus 8x. It'd be really tempting to write 12x down here. You'd be wrong. We want to write negative 4x because 4x minus 8x is negative 4x. Bring something down. Now I want to get rid of this negative 4x. If I put a negative 4 up here, negative 4 times x will give me negative 4x. Negative 4 times negative 1 gives me positive 4. I subtract, I get 0. That's a good thing because what that means is that this divides evenly into here, which I knew it should have because I already figured out 1 was a root. So what that tells me is that my function f of x is really equal to x minus 1 times negative 2x squared minus 8x minus 4. I'm trying to find the roots. Roots happen when this thing equals 0. Something times something equals 0. That happens if either x minus 1 equals 0 or negative 2x squared minus 8x minus 4 equals 0. If I solve this one, I'd get x equals 1, but now I'm just going around in circles. I already knew 1 was a root. That's how I knew x minus 1 was a factor. I'm trying to find the factors that come out from this term, the roots that come out from this. How do you solve this equation? Well, you have some options. Factoring when the leading coefficient is not a 1 is difficult. In fact, I even said that this one won't factor. On your test, I think I make it so this does factor if I remember right. So what do we do here? Well, I'd prefer this leading coefficient were a positive 1. You don't have to make it a positive 1, but I'd like to. So I'm going to divide both sides of the equation by negative 2 and get x squared plus 4x plus 2 equals 0. It's dividing both sides of the equation by negative 2. 0 divided by negative 2 is just 0. This equation I can solve. You could either use the quadratic equation, try to factor it. Oh, it doesn't factor. Use the quadratic equation if you want, or complete the square. If you were to complete the square, you'd start by getting your x squared and x terms next to each other. Then you'd make sure the coefficient on the x squared term is just a 1. Then you would add something to both sides of the equation so that you ended up with a perfect square on the left-hand side. In this case, it's 4 I want to add to both sides of the equation. Where this 4 came from is the same place this 1/4 came from. I called b 1. I said b over 2 squared is 1/4. Down here, my value of b, what the hell am I? Is not 1, it's 4. B equals 4. 4 divided by 2 is 2. 4 divided by 2 squared is 4. That's where this 4 right here comes from. Okay, so now I have a perfect square over here. X squared plus 4x plus 4 is the same as x plus 2 squared. And either this is x plus 2 squared because you recognize this is a perfect square, or because back at this stage you said b was equal to 4, and if you remember from above, this is always x plus b over 2 squared. b over 2 is 2. So I'm almost done here. I want to solve for x. I don't know where the hell I'm going to do this. Let's take this over here maybe. So the way I'll do that is I'll take the square root of both sides of the equation. Take the square root of the left and you get x plus 2. Take the square root of the right and you get the square root of 2. But make sure that you put in the plus or minus. And then finally, to solve for x, subtract 2 from both sides of the equation. And you get negative 2 plus or minus the square root of 2. Okay, so this is the answer for up here. I just ran out of room. And now I want you to sketch a graph. I'm going to have you sketch a graph. This one was a little bit hard to sketch a graph of because they end up with these square root of 2 things. So I gave this little note in here. On yours, I make them all end up being whole numbers because there's plenty of hard stuff on your test. I didn't want this one to be quite as hard. So what we got to do is we got to go back. We got to look at this thing and say the y-intercept is at 4. The reason the y-intercept is at 4 is because the y-intercept happens when x equals 0. If x is 0, these three terms are all 0. We're just left with the 4. Y-intercept is at this point right here. What else do I know? End behavior. It's a third degree polynomial, so that means it goes in different directions when I go to the left and to the right. And this negative kind of flipped things upside down. So what that means is when when I go to the left, it goes up. When I go to the right, it goes down. So there should be an arrow kind of pointing up in this direction and an arrow kind of pointing down in this direction, roughly speaking. But what happens in the middle is really what's most important. So I have a root at x equals 1, means it must go through this point. And then I got another root at -2 plus the square root of 2. Well, here's -2. If I add the square root of 2, the square root of 2 is a little less than 1.5. So if you add 1.5, you'd end up somewhere in here. If you start at -2 and you subtracted 1.5, you'd end up with this. So what I have, I'm going to erase those arrows, is a y-intercept here, an x-intercept here, here, and here. And I know that the end behavior starts me in this direction. Have to go through this point, turn around somewhere, where? You don't know where, wherever the hell you want. We'll figure out where in calculus. But at this point, we don't know where. So just turn around anywhere. Make sure it goes through those 3 points, through this intercept, and you get a very rough approximation to what the graph looks like. After calculus, you can learn more things like how steep things are and how far down this goes. But for now, we don't know that. So this is all we can do for our graph. One other point is I had 3 roots here. 1, 2, 3. And none of those roots repeated. The multiplicity of all of those roots was just 1, which is why the graph goes straight through those points. Had I made this problem work out that x plus 2 was, let's say we got x equals 1 here, and then we factored this thing out and got x equals 1 again. That would mean that the multiplicity of the root at 1 is 2. Anytime you have even multiplicity, instead of going through the graph, you bounce off at that point. I'm probably mentioning that for a reason. It didn't happen in this problem, but probably a reason I'm saying that. All right, question 5. We're given this mess of a polynomial and asked to find all of its roots. So what you need to know is roots are values of x that make the polynomial equal to 0. So essentially what I'm going to do is turn this into one huge equation. Set it equal to 0. How do you solve an equation like this? Well, it's not easy. We're going to have to do a lot of factoring. Fortunately, I give you some hints in here. Don't want to use polynomial long division. Instead, look for a greatest common factor. Okay, I'm going to stop there. 7 terms, 1, 2, 3, 4, 5, 6 terms. And I'm hoping they all have something in common. Well, you might notice that all of the coefficients are even, so I could factor out a 2. But I can actually do even better than that. They all have an x in them also. The greatest common factor between each of those 6 terms is 2x. And if you factor out 2x, what you'd be left with is x to the 6th power plus 2x to the 5th power plus 10x to the 4th power minus x squared minus 2x minus 10. Why does that help? Because generally speaking, adding up a bunch of stuff equals 0 is hard. But multiplying equals 0 is a little bit easier. The only way you can multiply together 2 things and have them equal 0 is if one of those 2 things equals 0. So at this stage I can say, all right, I have something times something equal to 0. So either the first one's equal to 0 or the second one's equal to 0. Well, I can solve this equation, divide both sides by 2, and you get x equals 0. There we go, we found a root. That's one of them. One down, a lot to go. How can I figure out when this thing equals 0? Well, it's a hard question. Maybe I gave you a hint. See, we already factored out the greatest common factor, then use factoring by grouping. Okay, so there's 6 terms. There's no greatest common factor between all 6 because I already pulled out the greatest common factor. But if I group them, if I thought about these first 3 as one group and these next 3 as the other group, I could pull out the greatest common factor, not from all 6, but just from the first 3. The greatest common factor between these first 3 terms is x to the 4th power. If I factor out x to the 4th power, I'm left with x squared plus 2x plus 10. I then look at my second group, and I have to factor out something so that I'm left with x squared plus 2x plus 10. Well, if I almost have it already, right? Negative x squared minus 2x minus 10, pretty damn similar. If you factor out a negative 1, you'll be left with x squared plus 2x plus 10. So what I now have are just two terms separated by this minus sign, and they both have an x squared plus 2x plus 10 in them. So I can factor that x squared plus 2x plus 10 out. Now this is gone and this is gone, and all I have is x to the fourth minus 1. I'm again in that nice situation where I have something times something equals 0. That can only happen if the first thing equals 0 or the second thing equals 0. Two equations to solve. How do you solve them? Well, let's see, there's one more hint. Recognize a difference of squares. Oh, right, x to the fourth minus 1, that's a difference of squares. I can factor that as x squared plus 1 times x squared minus 1. And if this times this equals 0, then either x squared plus 1 equals 0 or x squared minus 1 equals 0. What I now have are three equations left to solve. This one will kind of come out this way so I have some room. X squared plus 2x plus 10 equals 0. Try to factor it. Try to find two numbers that multiply to 10, add to 2. You won't be able to. Damn, it doesn't factor. Okay, I got two options then. Either use the quadratic equation or complete the square. I think people know how to use the quadratic equation, so I'm going to complete the square. I don't need to give you practice on stuff you can already do. X squared plus 2x equals negative 10. Remember, for completing the square, you want your x squared and your x term all by itself, and you want the leading coefficient to be a 1. Then add something to both sides, namely b, 2 in this case, b over 2 squared. 2 over 2 is 1, 1 squared is 1, so 1 is the number I want to add to both sides of the equation. The reason why is because what you'll be left with is a perfect square on the left-hand side of the equation. It'll always be x plus b over 2. b was 2, b over 2 is 1, squared. X plus 1 squared equals negative 9. Then x plus 1 equals plus or minus the square root of negative 9. Uh-oh, square root of negative 9. That used to be a problem. It's not anymore. The square root of negative 1 is just I. So the square root of negative 9 is 3i. So what we get is that x is equal to negative 1 plus or minus 3i. We've got these two complex roots here. One root, 2, 3 roots, and get 2 more here and 2 more here. For this one, subtract 1 from both sides, take the square root. X equals plus or minus the square root of negative 1, but we just said that the square root of negative 1 is I, so plus or minus I. And then x squared minus 1 equals 0. A couple different ways you can do that. You could either factor this, call it x plus 1 times x minus 1 equals 0, or you just add 1 to both sides, take the square root, and then get x equals plus or minus 1. 1, 2, 3, 4, 5, 6, 7 roots. That wasn't coincidental. There are 7 roots because this is a 7th degree polynomial. 7 total roots, real and complex. That'll always be true. B, completely factor this polynomial. That is, express it as a product of 7 linear terms. Okay, if, I know I've written this somewhere. If 1 is a root, x minus 1 is a factor. Anytime you have a root, x minus that thing is a factor. I can take advantage of that down here. I can say, wait a minute, 0 was a root? Then I guess x minus 0 must have been a factor. Negative 1 plus 3i was a root. That means x minus negative 1 plus 3i must be a factor. Negative 1 minus 3i was a root. All right, you get the point. Negative 1 minus 3i. I is a root. X minus I is a factor. Negative I is a root. X minus negative I is a factor. 1 is a root. X minus 1 is a factor. And finally, negative 1 is a root, so x plus 1 is a factor. Is that easy? This is your answer? Not quite, but almost. There might be a number here. A. How do you figure out what that number is? Well, what you can do is go up here. My leading coefficient had to be a 2. In order to end up with a 2 as my leading coefficient, when I multiply all these x's together, I'm going to get x to the 7th power, but I don't want x to the 7th power. I want 2x to the 7th power. Therefore, that a must be a 2. X minus 0 is just x, so we can write it like this. And then the rest of this stuff, I don't even want to recopy it. This is me being lazy. 2 times all this stuff would be the final answer. And yeah, you don't have to write x minus 0. You could just write x. Either way is totally fine. Okay, working backwards. I think these problems are interesting. Take that for what it's worth. I'm writing your final exam, and I think these problems are interesting. Anyways, it tells us that this right here is a third degree polynomial. It turns out that they needed to tell us that. Because just by looking at this, I can tell that there's a root at x equals, what is that, 3? And there's a root at x equals negative 2. And I know the multiplicity here is odd and the multiplicity is even here, because it bounces here, but it goes straight through here. But the multiplicity here might be 2, it might be 4, it might be 6. There's no way for me to know. But the sum of the multiplicities can't be more than 3. It's a third degree polynomial. What I'm getting at is this root at negative 2 must have a multiplicity of 2. And this one must have a multiplicity of 1. Because the sum of these multiplicities can't be more than 3. And this one's even. So it's got to be at least 2. And 2 and 1 gives us 3. Anyways, come up with this equation. Well, if 3 is a root, x minus 3 is a factor. If 2 is a root, x plus 2 is a factor. Oh, it's got multiplicity of 2. That means it must be a factor twice. So this is it. This is your answer. F of x equals this. Almost. There might be a number out in front, kind of like up here. Got to figure out what that number is. The way we can figure this out is the y-intercept looks like it's 1, 2 is 3. If the y-intercept is 3, that means when x equals 0, y equals 3. So what I'm saying is 3 must be equal to a times 0 minus 3 squared times 0 plus, oh, that 0 minus 3 shouldn't have been squared. Right, this is just 0 minus 3. The multiplicity here is just 1. It's the 0 plus 2 that has a multiplicity of 2. What I'm saying is 3 is equal to a times negative 3 times positive 4, negative 12a. In other words, a is equal to negative 3 divided by 12, which is negative 1/4. So my answer is that f of x equals negative 1/4 times x minus 3 times x plus 2 squared. So two-step process. First, figure out the factors by looking at the roots and make note of their multiplicity. Then use the y-intercept to figure out what the constant out in front is. Another working backwards one tells us that I have this parabola and its vertex is here. That actually gives us a lot of information. Parabola is a second degree polynomial. You could write it as a polynomial, like something x squared plus something x plus something. But it's hard to incorporate this information when it's written in that form. So instead I'm going to write it in vertex form. So I want to reference back to here. When it starts out like this, you can't tell a whole lot about where its vertex is. But if you can write it into this form, you can tell where its vertex is. I'm going to start out in this form right here, because once I have it in this form, I can tell what the vertex is. Or conversely, once I know what the vertex is, I can tell what b and c are equal to. So that's what I'm doing down here. If my vertex had an x-coordinate of 2, I must have moved to the right by 2. This must have been minus 2. If it had a y-coordinate of 3, I must have moved up by 3. This must have had a plus 3 at the end. The only thing I don't know is what the number out in front is. I can figure that out because I know that when x equals 3, y equals 1. So using this information, I know that 1 is equal to a times 3 minus 2 squared plus 3. Subtract 3 from both sides, you get negative 2 equals a, right? 3 minus 2 is 1, 1 squared is 1, so a is negative 2. And my answer is negative 2 times x minus 2 squared plus 3. So kind of like above, it's a two-step process. First, start in your vertex form, a times x plus b squared plus c. But then fill in b and c with what they're equal to. You can get that by looking at the vertex. Then figure out what a is equal to by using this information. When x equals 3, y equals 1. Change y into 1, x equal to 3, solve. This is the answer. All right, finally, I think this is the last one. I hope this is the last one. Yeah, last one, there's some extra credit. Find a 4th degree polynomial with integer coefficients that has roots of. Okay, if I know the root, God, I hate having to scroll up, but I've mentioned this a couple of times. If 1 is a root, x minus 1 is a factor. That's probably the most important sentence of Math 111. If something is a root, x minus that something is a factor. So if 2 plus 3i is a root, x minus 2 plus 3i is a factor. If 2 minus 3i is a root, x minus 2 minus 3i is a factor. And then finally, if 0 is a root, x minus 0, in other words, x, is a factor. Oh, it's got multiplicity too? Better throw a squared up there. So find a 4th degree polynomial. Well, here's a 4th degree polynomial, kind of. I mean, this is the factored form, but it doesn't have integer coefficients because I still got all these i's in here. In other words, all this problem is asking you to do is multiply this mess together. It's actually not that easy. We'll start by multiplying these two together. You can do that in a couple different ways. Okay, I'm going to do it the way I think is easier. X minus 2 minus 3i, x minus 2 plus 3i, x squared. I took these negatives and distributed them through. X minus 0 is just x. I'm going to multiply these two things together. When you're multiplying polynomials, I mean, essentially you're using FOIL, but that acronym only works when it's 2 terms times 2 terms. So what I do is kind of an extension of FOIL is this thing that I call the box method. Take one of the polynomials that you're trying to multiply and you write them as the headers for columns, and the other you kind of write them as the rows. And then you create these boxes, make this grid. And you multiply each one individually, and that'll tell you what the product of these two polynomials is. So x times x, that's just x squared. X times negative 2, that's negative 2x. X times negative 3i, I guess that would be negative 3ix. Weird, don't worry about it, it'll go away. X times negative 2, negative 2x. Negative 2 times negative 2, positive 4. Negative 2 times negative 3i will be positive 6i. X times 3i would be 3ix. Note that this and this will cancel. 3i times negative 2 is negative 6i. Note that this and this will cancel. 3i times negative 3i is negative 9i squared, which is the same as positive 9 because I squared is just negative 1. What I'm saying is that when you multiply this times this, what you get is x squared minus 4x, these guys right here, plus 4 and 9 gives me 13. What about all the rest of this stuff? These two cancel each other out, and these two cancel each other out. Oh, and then I got to multiply that by x squared. Fortunately, multiplying by x squared is easy. We get x to the 4th minus 4x cubed plus 13x squared as my polynomial. Finally, extra credit questions. I guess I should do it. I've come this far. The basic idea here, I kind of tell you this. I tell you why this problem was worth doing. This average rate of change when one of the points is a and the other is a plus h, turns out it's important. It's calculus. I'm giving you a problem. This is a problem. It's a hard problem. It's a problem I put on quizzes in calculus classes. We can do it without being in a calculus class. It really all it depends on is the average rate of change stuff. And so what I'm going to do is I'm going to use my average rate of change formula a bunch of times. My x1 is always a, my x2 is always a plus h. So This is always a plus h. This is always a plus h minus a. I'm always going to have an h in the denominator. That's a plus h minus a. And then in the numerator, well, y2 is f of x2. So it's a plus h cubed. And y1 is f of x1. Well, it's a cubed. And if you expand this out, a plus h cubed, a plus h times a plus h times a plus h, what you'll get is a cubed plus 3a squared h plus 3ah squared plus h cubed. And you got minus a cubed for this guy divided by h. The goal in calculus is you want to change all the h's into zeros, but you can't do it right now because you can't divide by 0. But this a cubed and this a cubed cancel out. So I get 3a squared h plus 3ah squared plus h cubed over h. And now each term in the numerator has an h in it. So I can factor out an h from each of these three terms and cancel it with this h. And I'm left with just 3a squared plus 3ah plus h squared. If I just asked you to find the average rate of change, you'd be done right here. But if you follow these instructions, it says, then change all the h's into zeros. If you change all the h's into zeros, this would go away, this would go away, and we get 3a squared. Turns out that is the derivative of x cubed. This will be important in calculus. Do that a couple more times. God, these are brutal. Same idea. I get 1 over a plus h minus 1 over a divided by a plus h minus a. And I want to simplify this mess. To get a common denominator, I'll multiply this by a over a. Give me a times a plus h. And I'll multiply this one by a plus h over a plus h. Now that I have a common denominator, I can put these two fractions together. A minus a plus h. A minus a cancels out. I get negative h on the top, and then a times a plus h on the bottom, this common denominator. That whole thing is divided by h, which I'm going to write as h over 1, because when you're dividing fractions, you can rewrite that as multiplying fractions. And these h's cancel, and I get negative 1 over a times a plus h, which if I make my h a 0, I get negative 1 over a times a, or negative 1 over a squared. Turns out that that's the derivative of this guy. These are pretty hard. I gave you an extra credit question on your test. It's not as hard as these. One last time. The square root y2 would be take a plus h and put it into this function, square root of a plus h, minus square root of a divided by h. There's a trick when you are trying... Okay, so up here I said finally replace all the a's with x's. So I guess I should have made this 3x squared. And I should have made this negative 1 over x squared. Just says in the last step, instead of writing it like this, write it like this. Whatever. If you got here, I'd give you full credit. You get here, I want to cancel out this h. There's a little trick to it. You multiply the top and the bottom by the conjugate of the top. You got a fraction, so you can always multiply the top and the bottom of a fraction by the same thing without changing its value. I'm going to choose this as the thing, because if I multiply the top and the bottom by this, things will cancel out really nicely. Square root of a plus h times the square root of a plus h is just a plus h. Those square roots cancel. This times this is the same as this times this, except one of them's negative, one of them's positive, so those cancel out. Negative square root of a times square root of a is just negative a. So I get here. But now the two a's cancel, so I'll show another step. So I get h divided by h times this mess. But now the two h's cancel. So I get 1 divided by the square root of a plus h plus the square root of a, which if I change all the h's into zeros, I get 1 over the square root of a plus the square root of a. In other words, 1 over 2 square root of a, which if I change the a's into x's, I'd get 1 over 2 square root of x. I've been putting boxes around with the a's in them, but really the final answer should have the x's in them. This is the derivative of this function. These are not easy calculus questions. And I put them on here for extra credit to kind of show that, what you'll see in calculus really won't be that different than what we're doing in Math 111. But I think that's finally the end of this video. I think that went on a little bit too long, but hopefully it helps people with studying. I'm going to send you an email right now with more information about the final, and then I will see you for the final.